Hello, today we are going to talk about survival and time to event concepts. In strict dictionary form, survival is the fact of living or continuing to live longer than another person or another animal. But in epidemiology, survival analysis is a set of statistical techniques used to investigate the time it takes for an event of interest to occur. And the term survival, it's used because the methods were firstly developed to investigate mortality. This kind of statistics could go very fancy and very complicated, but today we are going to talk only precise, concise concept levels of the survival analysis. A key parameter of interest in veterinary epidemiology is the time until the occurrence of an event such as death or infection or onset of a disease, or also for good things like recovery from disease or giving birth or calving or lambing and so on. And the basic idea is when does the event occur and whether the event occurs or not. And so we have these two variables, let's say time variable and a variable registering the event happening or not happening. And basically the when concept is just depicting the amount of time that it will pass before the event occurs. But in order to quantify such phenomenon, when and if it happens or not, what kind of techniques do we have available to measure such data? One way to quantify time to event is to use the average time. And the average time is calculated only for the animals which have experienced the event of interest, and not to the other animals which did not have the event of interest. So it's limited only to this subgroup of animals and cannot take into account the others which didn't have it. On the other hand, there is also a problem with using average time because the mean can be affected by the very low or the very large time intervals. So, for example, if we use a short time interval to follow up, we might have an underestimated time to event of the occurrence of that event. On the other hand, if we have longer periods, and especially if we have animals which take a long time to develop the event of interest, that would cause a distortion in the mean because the mean itself is very sensitive to extreme values. Another measure would be the median time to event. So this is much better in terms because it's not affected by the extreme values. But on the other hand, it needs to be computed if we have more than 50% of the animals experiencing the event of interest. And then another way would be to use the incidence rate. And the incidence rate, it takes into account that the rate is constant over time, but that's not the case in reality because the rates change due to different factors. And the best methods to calculate or to quantify basically the time to event is the survivor and the hazard function. The survival is the probability of individuals with a specific disease or event of interest which remain alive for a specified length of time. And in principle, survival is the complement of case fatality. And therefore, for a given period of observation, the sum of case fatality and the survival should be equal to 1, or let's say 100%. The formula to calculate the survival is the number of exposed or new cases during the same period of time minus the number of events observed in a specified period of time above the number of exposed cases or new cases during the same period of time. The survival function is the cumulative survival probability, and it shows a distribution that the cumulative proportion of individuals not having experienced the event of interest over the time at risk, so during the period of study. And it is a value which is not increasing and it ranges from 1 to 0 and usually starts at 100%. So at the beginning of the study, all animals are alive, let's say, and then with time, some of them die, so the probability goes down and can reach also 0 if all animals die. While the hazard function shows the distribution patterns of the hazard rate, and which is also considered as force of mortality. And the hazard rate can be calculated as a probability of an animal experiencing an event during a specified time above the length of time of the interval which we are studying. Let's say a month or a day or 6 months, or depending by the interval we check in to identify the event happening. Both methods can include into their calculation also the animals which did not experience the event of interest. So unlike the mean, which we could calculate only the time of the animals which had experienced the event, in this case we could calculate the time also of the animals not having the event of interest. And the outcomes of such methods is that the resulting quantities are risk and rates, which are very convenient in interpreting further in the epidemiological analysis. And when we say about the animals which did not experience the event of interest, this we called censored animals. And the censoring concept is like defined as the occurrence or possible occurrence of an event when the animal is not under observation. And to make that more clear, it's, let's say, when the study ends, the animal might have that event, but it's beyond what we are looking in the study period. Or let's say the animal was lost to follow up, I mean it was sold or so on. And this is generally called right-censoring, and this is the one which we'll focus more today. But there are also other ways of censoring, which is interval-censoring. For example, we do check in different time periods to identify animals with the event. Let's say each 6 months we follow up a flock and see if any animal died. But in a time period we find out and realize that an animal died, so we don't know the exact momentum when the animal dies because it's 6 months, and we would say it has occurred between the interval 1 to 2 or 2 to 3, so it depends by the interval between them to identify where that animal. So then we censor that slice of time. And in a similar fashion, it works also for left censoring, but in this case, it might be that the animal have had the event of interest before the study started. So that's a left censoring, but if the disease, for example, it's reoccurring or it's something that we are measuring in a different time, it's reoccurring basically different times. Let's say mastitis could happen several times in a life of an animal. We call that as a truncation, but we'll talk into a different lecture about truncation, and for today we'll focus mainly only on the right censoring. Let's take an example of anthrax in Georgia. And this disease in Georgia country, it's endemic and it's highly prevalent in the south of the country. So we'll follow a herd of 10 cattle, let's say the population at risk, which is enrolled in our study for a period of 12 months. However, we have to take into account that all animals are exposed into a contaminated pasture and have all the same identical chance to contract anthrax. And we set this up into one of the southern districts with the high incidence of the disease, and we might experience many cases during the year. And let's see a bit the cases here. We construct a table with the number of months, and let's say animal A had the disease at the 5th month in May, and then animal B survived all along the study. Animal C was removed from the study. Animal D had the disease in February 2nd month. Animal E lived all throughout the study, and we don't know if the event has occurred beyond the year because that's our time scale. Animal F and G had the 6th and the 11th month respectively the disease and died out, and then animal H and I survived through the whole period of study, while animal J was removed from the flock at the 6th month. Now, to trace the timing and the animals and what's happening, we construct a table which is below this graphic of the timing. And let's check that the rows, events, and removed represent the animals which are withdrawn or died respectively. So the events are the animals which died from anthrax, while the removed are the animals which are removed from the study for different reasons. In the row at risk is shown the number of animals at risk during a particular month, and animals which have died in the previous month or were withdrawn at the end of the previous month are to be subtracted. In the duration row, it's represented the length of the respective follow-up interval, and in our case it's 1 month. While we say in the survival probabilities, it uses the event row as a numerator and the at-risk row as a denominator for its own calculation. So during a particular month, we would have a conditional survival probability calculated between events above the animals at risk, and that's the probability of survival. When we have an event probability, basically it's 1 minus the conditional probability, while the hazard rate is the quotient between the row, conditional event probability, and the row duration, representing the length of the respective follow-up interval, which in our case it's 1. So the hazard rate in this case would be equal to event probability, because the timing is 1. And in the cumulative survival probability is the product of all conditional survival probabilities expressed as a cumulative survival probability. Let's make the first month the calculation, and we put the figures down in the table. We read it in the first column, and we have 0 removed and 0 events. So we have no animals leaving out the study, and we have no cases happening. The animals at risk, it's 10 again, so the whole population, and the duration is 1 month. While the survival probability is 100%, we have 0% of an event and of course 0% of hazard rate. And then the cumulative survival probability for the first month of the study, it's again 100%. But in the second month, we had the case. So in February, an animal died, and as usually with anthrax, a sudden death occurred, and the vet would go there and do the diagnostic, and we proved out that this is an anthrax case. And we do the second row, the second column, in the second column we count the numbers and we do the math, and we see that the removed is 0, the event is 1 because we have 1 case, and then the duration is as usual 1 month because we are checking in each month, and then the survival probability is 90%, the event probability is 10%, the hazard rate 10%, and the cumulative survival probability is 90%. Now, to calculate the survival probability, we use the concept we mentioned, that we say the animals at risk minus the event, the number having the event above the at risk, and it will give us 90%. And the hazard rate in this case is survival probability above the duration, which is 10% above 1, which is yielding 10% again. And so on, we continue with the calculation, and we, let's say, go up to the second case occurring in May, on the 5th month, and then we keep note of the data, and we say 0 animal removed for this period, we have 1 event again, and we have the population at risk 9 animals, and we have a duration of 1 month as usual, and the survival probability, it's going down to 0.89, so it's 89%, and then we have an event probability of 11% and hazard rate of 11%. The cumulative survival probability now goes to 80%. And the calculation of the cumulative survival probability, as we mentioned, it's a product of survival probabilities. And so it takes into account all the survival probabilities time one after another and gives this product. We continue with the calculations and we find out that one of the animals was sold out in the market. And normally that's the usual life into a farm. Animals come in and animals goes out, or animals die for other reason. And so the reasons for censoring basically could be a withdrawal. For example, the farmer would say, no, we won't follow anymore this animal, and so he's withdrawing his consent to follow up the study with that animal. But it could lose to follow up because the animal, as in this case, it's sold out in the market, so we lost the follow-up. But it could happen also about competing risks, so animals dies from other reasons or other diseases. And another reason for censoring is that the study finishes and all the animals which did not experience the event of interest at the closeout of the study will be naturally censored. And when we do the censoring and the events, we change the number at risk. And if we see in the row at number at risk, we have in the 7th month from 8, we have now 6 animals. So the population at risk has been reduced because we had from the previous month, let's say from June, we had 8 animals at risk, and then we have to subtract 1 animal which had the event, which died, and 1 animal which was sold out. So that would leave us in the July with 6 animals. And so on, we continue following up the whole herd of cows in the infected meadows with anthrax spores, and we go till to the end of the study. And we see that at the end of the study, the whole cumulative survival probability of a flock of the herd has been dropped down from 100% in the first month to 56% in the last month. We could further on draw lines or draw graphs about the hazard rate and the cumulative survival probability, so you see them depicted, and you will most oftenly check this kind of graphs in most of the published literature for survival analysis, and you'll see many published papers. And so that's how such kind of graphs are derived for. So nowadays, of course, it's not needed to do all the math by hand because computer packages could easily do. So if we have properly counted and take note about the timing and the events happening, there are plenty of statistical packages for computers which could produce all fancy statistics and also the graphs. And in our case, we have this kind of graph that we started at 100% and we finished up at 56%. And the probability, this is the probability of a cow to survive from anthrax in an infected or contaminated pasture beyond 1 year. It would be, as we said, 56%. While the hazard function shows the force of mortality, or let's say the rate of death of an animal at a given time, and so we see that depicted in the graph in red. And this is all in terms of concepts about survival and time to event data. We'll talk more about rates and ratios and other measures of disease frequency and occurrence in the next lecture. And till then, be safe and see you next time.